Good morning, and welcome to our This is the short course, PJLA and I believe there's also a 16-hour version. So anyway, welcome to our presentation. I want to tell you a little bit about PJLA. I'm displaying now the contact numbers. Contact in the United States is the first address. Contact in Great Britain is the second. Phone numbers are current, web address, and so forth for the PJLA website. PJLA was founded and formed in 1999, and it is an ILAC MRA signatory. As such, it is an internationally recognized accrediting body providing accreditation services to calibration and testing laboratories in many countries throughout the world, now including Great Britain. In addition to this free short course on measurement uncertainty fundamentals, PJLA routinely offers customer and public training programs on a variety of topics related to the 17025 standard in its most current form, 2017, and also they deal with how to properly implement it in your laboratory. The PJLA website includes a schedule of upcoming training plus recordings of instructional webinars on a variety of topics related to the 17025 standard. Today's training is intended to provide you with useful fundamental knowledge of measurement uncertainty and the methods used to estimate the uncertainty of calibration or testing results. My name is Henry Alexander. I am the trainer for today. Here's a little bit of biographical information. I'm a certified manufacturing engineer as well as a certified quality engineer, and I am the former PJLA calibration program manager. I am a senior metrologist at my own business, Henry Alexander Engineering Incorporated. I am a degreed mechanical engineer. More importantly, I'm a tool and die maker. I'm a lieutenant, or I was a lieutenant, I'm now retired, in the U.S. Army 612th Combat Engineer Battalion, 416th Combat Engineer Group. My hobbies and interests, I build miniature stationary steam engines. I'm currently working on one that will fit inside a standard light bulb for display purposes. I'm learning to play golf now that I'm semi-retired. Not very good at it, but I enjoy it, have a lot of fun. I also have always had a lifelong love affair with cars, and so I'm going to show you a couple pictures of my car. This is a 1951 Henry J that I built to look like a gasser racing in the gas and sedan classes, drag racing back in the late 60s and early 70s when I was growing up. It has a 600 horsepower small block Chevy engine. As you can see, it's got a supercharger and interly fuel injection. I don't race the car, it's strictly street driven, but I spent about 6 years building it, a lot of time, a lot of money, but I've had a lot of fun too. Really enjoyed it. So that's a little bit about me. The schedule of activity for today. The training will be approximately 2 hours in duration. The question and answer period will follow the second hour. So keep note of any questions we have, and we'll have time. There will be 7 interactive quizzes during the course of training. Primarily, these will just be questions on information that was previously presented, and you can select an answer. A poll of possible answers will be displayed on screen, and you are to select what you believe to be the correct answer. After you have had a chance to make your selection, the correct answer will be identified, and we'll have whatever discussion is necessary to clarify that. Today's presentation will be recorded and available on the PJLA website for review or download, and a certificate of completion will be issued by email to all participants several days after the training is complete. This is important since it's necessary during assessment to be able to show evidence of training for the activities you're involved with. So certificates showing that you participated in this presentation today would be helpful in that purpose. Let's begin. This document, JCGM 100 2008, is the Evaluation of Measurement Data Guide to the Expression of Uncertainty in Measurement. GUM, Guide to Uncertainty in Measurements, commonly referred to in the industry as the GUM. And this is a very in-depth, comprehensive presentation of measurement uncertainty. I wouldn't recommend that you read this after a long day when you're sitting down, because it'll put you to sleep pretty quickly. It is interesting from the perspective that it presents the statistical mathematical basis for measurement analysis. It's a very good reference source. I've given you at the bottom of this slide the address where you can go and obtain a copy of this. It's free at no charge from the BIPM website, and it's a very useful document to have on hand. Another important document, JCGM 200 2012, the International Vocabulary of Metrology, Basic and General Concepts and Associated Terms. Again, I've given you the website at the bottom of the page. It's the same website, but it's a different location on that website where you can download this document. And this is important because it defines the terms that are pretty much unique to metrology and what they mean. So when we talk about calibration, as an example, that means what the VIM says it means. And the VIM is, again, the International Vocabulary of Metrology. And when we start talking about the fine points of why we do what we do, or how to do particular activities, again, perhaps estimating measurement uncertainty, positions we take and the methods we use need to be expressed in terms that everyone in the industry will understand. So the VIM is the common collection of the terms used in metrology and what they mean. So in other areas of endeavor, they may mean something entirely different. When we're working with metrology, though, we're interested in the definitions of the terms as they are found in the VIM. Again, I would recommend, especially since this is a free download, that you go to the BIPM website and download a copy of this as well. Now let's look at the requirements related to measurement uncertainty that are found in the standards and references that we have to work with. Measurement uncertainty requirements in the 17025 standard. Now, when we're talking about the standard today, unless it's a measurement standard, and I'll try to identify those, we'll be referring to the ISO IEC 17025-2017 standard. The 2005 standard will be totally obsolete as of the 29th of November this year. Everyone needs to be, if you're accredited or in the process, you need to be working with 2017, that version of the standard for accreditation. Measurement uncertainty requirements in ILAC P14, and ILAC is the International Laboratory Accreditation Cooperation. They publish a series of documents. There's some guidance documents, which are G series. There are some policy documents, which are, or procedural documents, which are P series. P series documents will be imposed on laboratories through the accrediting body. ILAC publishes a procedural document. The accrediting bodies are obligated to ensure that the laboratories they accredit operate in compliance with the ILAC procedural document. So we'll be looking at some of the issues and some of the requirements found in P14 related to measurement uncertainty. Measurement uncertainty requirements found in the GUM, we're going to look at some of those. Measurement uncertainty requirements in PJLA PL3. Now, if you are accredited by Perry Johnson Laboratory Accreditation, PJLA, this is a document that you would have to be familiar with. You'd have to have it on hand in your laboratory so you can access it at any time. You'll have to make sure that you stay current with it as they update the document. You'll need to monitor the website periodically to make sure you have the most current version. But this is Perry Johnson's policy on measurement uncertainty. So the things that the accrediting body, in this case PJLA, requires you to do relative to measurement uncertainty are defined in this document. For those of you who either are not yet accredited or perhaps are accredited by another accrediting body, this would not apply. However, that accrediting body would have their own series of policy documents, and I can assure you that they would address measurement uncertainty in one of those. Seems a little overwhelming and to get buried in documentation and stuff. It really isn't that way. It's like any other topic. There's information you need to learn, you need to become familiar with, so that you're not having to look it up every time you use it. But it's common in that it's related, one document related to the other, and the requirements complement one another. And when taken together, it forms the body of restraints that are placed on laboratories in terms of how they estimate uncertainty, when they estimate uncertainty, and the methods that they use to do so. All right, let's look at requirements found in the standard, the ISO standard. And again, be sure you're working with the 2017 version. In section 7.6.1 of the standard, it says laboratories shall identify the contributions to measurement uncertainty. When evaluating measurement uncertainty, all contributions which are of significance, including those arising from sampling, shall be taken into account using appropriate methods and analysis. Now, this is taken verbatim from the 2017 standard. We talk about contributions. That word came up several times here. What that's talking about is you have an overall measurement uncertainty that is the result of uncertainty from a number of different sources or contributors. Each of those sources contributes some amount to the total measurement uncertainty. So when we talk about contributing or contributions, keep that thought in mind, that that's the amount of uncertainty applied to the total from one particular source or contributor. Here's our first question then. When evaluating the uncertainty of measurement results, what uncertainty sources must be included in the analysis? And there's 4 answers that you can select from. All that can be easily identified, all that are of significance, all that are identified in the standard, and customer requested sources listed on the purchase order. So from what we've already talked about, pick what you believe to be the correct answer in the poll that's on screen now. We'll give you just a little bit of time to do that. Okay, everyone should have been able to make a selection at this point. So let's move on and look at the answer and discuss it if we need to. When evaluating the uncertainty of measurement results, what uncertainty sources must be included in the analysis? That was the question. The answer is all that are of significance. All that are of significance. Again, the verbatim extract from the standard, laboratories shall identify the contributions to measurement uncertainty. When evaluating measurement uncertainty, all contributions which are of significance, including those arising from sampling, shall be taken into account using appropriate methods of analysis. So if a contributor is insignificant, then it doesn't have to be included. So this begs the question, how do we know what's significant and what is not significant? Again, for those of you who are accredited by PJLA or are considering pursuing accreditation through them, PL3, the Perry-Johnson procedure for measurement uncertainty, requires that your uncertainty procedure, which is a requirement of the standard that you have a procedure, PJLA says that your uncertainty procedure must contain a significance test. In other words, it must identify the means by which you select which contributors are significant and which ones are not. There's very little publication on this. It's one of those things where professionals working in the metrology industry should have an awareness of what is significant and what isn't. But for those of you who are interested, I'm going to give you a rule of thumb that I use myself when I have my own laboratory and in consultation with other labs. If one or more contributors to the overall uncertainty of a result taken as individuals or taken as a group of small contributors, contribute no more than 1% of the total, then they can be considered as insignificant. So again, an individual contributor taken by itself or several contributors taken together do not contribute more than 1% to the total. That individual or that group of individuals can be considered as insignificant. What that means then is everything left has to be considered as significant and included in the analysis. There are literally thousands of potential contributors to uncertainty. And for instance, in calibrating mass, the phase of the moon is a contributor to uncertainty. If it is significant, it has to be included. In almost all instances, it is not significant, especially if you're working with commercial grade weights as opposed to high precision laboratory grade weights. The point is that, if you stand too close to the machine, that's potentially a contributor to uncertainty, depending on what the machine is doing. If it's a precision length measuring machine, anything that that adds heat to it is a contributor to uncertainty. The point is, you have to recognize some contributors are large and are significant. In some instances, you'll have one, possibly two, that contribute almost the majority of all uncertainty, and everything else is relatively small, and some would be insignificant. So develop a significance test that you can apply and eliminate those that are insignificant, so that it reduces measurement uncertainty analysis to typically being 4, 5, maybe 6 individual contributors, and many others that you don't have to consider because they are deemed to be insignificant. 7.6.1, we just read that, so we'll go on past that. But there's 3 in succession that you want to be familiar with coming out of the standard. 7.6.2, a laboratory performing calibrations, including of its own equipment, shall evaluate the measurement uncertainty for all calibrations. So this is speaking specifically to calibration laboratories and that are calibrating equipment. Even if it's their own equipment, they still have to evaluate measurement uncertainty for all calibrations. Every calibration they do, even if they calibrate the same device year by year by year, the uncertainty is expected to be slightly different from time to time because of the random variations, typically not systematic variations, but random variation contributes to that. Non-repeatability, doesn't get exactly the same answer on a measurement from year to year. So every year that you would calibrate that machine, you have to estimate its uncertainty under the conditions that exist at that particular time. 7.6.3, a laboratory performing testing shall evaluate measurement uncertainty. Now you notice the language changes between calibration laboratories in 7.6.2, testing laboratories in 7.6.3. Testing, depending on the particular test, you might be testing powders that form pharmaceutical tablets or something of that nature. You also might be doing dimensional inspection using a coordinate measuring machine. Those would both be tests, and measurement uncertainty potentially would be handled differently for both because of the nature of the materials, the nature of the test itself, the nature of the environmental conditions under which the test is being performed. Testing is broader based in terms of how measurement uncertainty is addressed. Calibration is very specific. If you perform a calibration and report the results, you must estimate the measurement uncertainty specific and unique to that calibration. 7.6.3 note 1. In those cases, now this is testing again, in those cases where a well-recognized test method specifies limits to the values of the major sources, that would be the significant contributors, major sources of measurement uncertainty, and specifies the form of presentation of the calculated results, the laboratory is considered to have satisfied 7.6.3 by following the test method and reporting instructions. So again, in tests, there are instances where the test method and procedure and equipment is well recognized, agreed to industry-wide, and used essentially throughout the world to perform the specific test of the specific material. If a laboratory follows the procedure, and uses appropriate equipment, trained technicians, and so forth, then typically they don't have to estimate uncertainty independent of that because it's built into the development of acceptance criteria. All elements of the test and components of the equipment are potential sources of uncertainty. Detailed specification of the test apparatus is provided. Many times, for instance, in the ASTM standard, it will give you dimensions for the components of the test equipment. It'll give you length, distance between holes. It might give you material specifications. So if it's something where force is applied, that a predictable amount of distortion of equipment produced by the application of that force can be understood and calculated, at least from a theoretical perspective. But the test apparatus is well defined. Now, the small unit by unit variation that occurs in manufacture is one of the contributors to uncertainty of measurement with these pieces of equipment. Specific instructions are given for performance of the test. In other words, the manner in which the test is performed is detailed by specific step-by-step instructions, and the expectation is that those instructions will be followed as published every time a test is performed. Stated limits to the values of major sources or contributors of measurement uncertainty are typically based on the statistical analysis of data from tests within the applicable range of the test method. In other words, if the test method is good from some small magnitude to a large magnitude, then in the development of a published, internationally recognized test procedure, measurements or tests would be performed at the low end of the range, at the high end of the range, and various points between those. And that data would have statistical analysis applied, and from that would be test limits or acceptance criteria developed that would be used in determining suitability of the device or the material tested. Okay, 7.6.3, note 2. Keep in mind 7.6.3 related to testing laboratories rather than calibration. For a particular method where the measurement uncertainty of the results has been established and verified, there is no need to evaluate measurement uncertainty for each result if the laboratory can demonstrate that the identified critical influencing factors are under control. In other words, if the identified significant contributors of measurement uncertainty can be proven to be under control, and typically this is talking about statistical control, SPC, for instance, statistical process control. If you can determine that the significant contributors are under control statistically, then you don't have to estimate uncertainty every time you perform the test. You can estimate it under carefully controlled conditions with all the significant contributors being able to be proven to be in control, and apply that uncertainty to that test every time you perform it. Now, obviously, if the test changes dramatically, different equipment introduced or something of that nature, this would not apply. But as long as you're doing the same test, using the same equipment, following the same procedure, this does apply. Be aware that Note 2 applies to testing laboratories only, not calibration laboratories, testing labs only. 7.6.2 requires calibration laboratories to evaluate measurement uncertainty for all calibrations. 7.6.3, Note 3, gives you a source for additional information on this topic. Guide 98-3, ISO 21748, and the ISO 5725 series of documents. All right, true or false question. This is question number 2. For a calibration laboratory, there is no need to evaluate measurement uncertainty for each calibration result if the laboratory estimated at once and can demonstrate that the identified critical influencing factors are under control. So again, this would mean if you can determine that the significant contributors to uncertainty are under control. All right, the poll is open. Make your choice of what you believe to be a correct answer. We'll give you a little bit of time to do that. Not a lot, because it's a simple response. Okay, let's close the poll and move on. Is this true or false? False. And the reason it's false is because what we talked about with being able to estimate the uncertainty, maintain control of all the contributors, and then take that estimated uncertainty and apply it time after time after time applies only to testing laboratories, only to testing laboratories. Calibration laboratories, it doesn't apply. And here's again the note. This is taken verbatim from the standard. A laboratory performing testing. Note 2. For a particular method where the measurement uncertainty of the results has been established and verified, there is no need to evaluate measurement uncertainty for each result if the laboratory can demonstrate that the identified critical influencing factors are under control. Testing laboratories only. I want to emphasize that. Be aware that Note 2 applies to testing laboratories only. And remember, calibration laboratories, every time a calibration is performed, an estimate of the uncertainty associated with the results is mandatory, has to be done. All right, let's look at ILAC P14 and some of those restrictions or requirements there. Uncertainty resulting from repeatability must be included in the estimate. When we talk about repeatability, in reality, we're talking about non-repeatability. We're interested in the extent to which an instrument or a piece of equipment will not repeat a measurement. And there's uncertainty associated with that. And ILAC P14 requires that repeatability must be included in the estimate. Regardless of the reporting option chosen, and this goes back, that's a holdover somewhat from the 2005 version of the standard. Regardless of the option chosen, the uncertainty would have to be, if the unit under test will be used to perform further calibrations, the uncertainty must always be reported. Under 2005, which some laboratories are still operating under until they transition prior to November 29th, so we need to mention this. If the device being calibrated will itself be used to perform further calibrations, then it's mandatory that the uncertainty be on the certificate. If it will not be used for further calibrations, then the uncertainty has to be estimated and either reported on the certificate, or it can be used to make a statement of compliance with specification. But in either case, if it's on the certificate because it must be, or if it isn't there because a statement of compliance was made and the customer didn't ask for it or didn't say they needed it on the certificate, the laboratory has to estimate it and have that information readily available. In other words, they don't estimate it when they get the call saying that a customer needs it. They estimate it at the time of the calibration, and if a customer calls and says, I need it, it is readily available. So keep in mind that it doesn't reduce the work that's done, it simply reduces the ink that you use in printing the certificate. All right, uncertainty and CMC must both be estimated by the same method. It's important for us to talk a little bit about CMC. This stands for calibration and measurement capability. This used to be referred to as best measurement capability, BMC. And what it says in ILAC P14 is that when you're estimating the uncertainty of measurement for a calibration you performed, or when you're estimating the calibration and measurement capability of your laboratory, those estimates must both be done by the same method. CMC is the hypothetical state of the uncertainty that occurs when you're calibrating the very best piece of equipment under ideal conditions. So if you're estimating uncertainty, you're going to be maybe close to ideal conditions, but not quite. And you're going to have a very good piece of equipment you're calibrating, but in all likelihood, it's not the very best in the world. So the estimate of CMC takes into account the performance of the best existing device, best in class. And so it is an estimate of uncertainty, but it's hypothetical in that the conditions under which it's estimated rarely actually exist. You may get very close to them, but not quite there. So that That brings up this next one. The uncertainty must never be reported as less than the CMC for the ability of the laboratory to perform the calibration. If you're properly estimating the uncertainty and the CMC, then it cannot possibly be better than the CMC, because the CMC, again, would be the very best equipment under ideal conditions. The uncertainty shall never be reported at more than 2 significant digits. Now, in PJLA PL3, this is a requirement, and a method is specified for rounding numbers properly to 2 significant digits. And a calculator is available to do this from the Perry Johnson website. It's a custom Excel spreadsheet application. It happens to be one that I developed when I was the program manager, but it's available on the website for free download, and it has the Perry Johnson specified decision rule as to how to round. That's built into the calculator. So if you use it, you will always get the acceptable result for Perry Johnson. All right, let's look at the GUM and its requirements. All contributors of significance must be taken into account. We've heard that before. Keep in mind that it's necessary that you have some means of determining what is significant and must be included and what is insignificant and can be excluded. We talked about an acceptance test. You can either use the rule of thumb test that I had stated to you before if you like it. If not, develop your own, but you have to be able to consistently select what's significant and what's insignificant. All contributors must be evaluated using appropriate mathematical and statistical techniques, and we'll talk about some of those in the second hour. Repeatability, or as I mentioned, non-repeatability, inability to repeat. Repeatability is represented by the experimental standard deviation of the mean. In other words, the mean of a sampling distribution rather than the mean of a distribution of individuals. We'll talk about this later on also. There's a specific formula for how to calculate it. The best approximation of the actual value of the measured value of interest is the average of repeated readings. So you take multiple readings and average those and report that average as the actual value. The larger the number of measurements you take and then average, the closer you get to the actual repeatable measured value. Type A analysis. You'll often hear that an estimate of uncertainty contribution for a particular source came from a type A analysis. Type A is statistical. For instance, the one we talked about for non-repeatability, where you're taking multiple numbers and averaging those, that's actually a statistical operation, and that would be a type A analysis. A type B analysis is when the result is obtained by any other method. In other words, if a method is not statistical, no matter what it is, it's type B. If it is statistical, then it's type A. Keep that in mind. There are no type A uncertainties and type B uncertainties resulting from particular contributors. Type A is statistical. Type B is when analysis is obtained by any method other than statistical. Okay, let's talk a little bit about the requirements of PJLA PL3. We've already talked about that in light of the other standards and documents. So let's talk about this one a little bit. And some of this may be redundant. This is the example of the policy of an accrediting body, because some of you may not be accredited with PJLA, and that's fine. But whoever your accrediting body is, they will have their own policy of how to deal with measurement uncertainty. Uncertainty analysis is to be documented in an uncertainty budget. Nowhere in the standard does it require you to have an uncertainty budget, but at PJLA, you have to document the information somehow, and rather than just writing it on the back of a cocktail napkin, Perry Johnson said you need to develop an uncertainty budget. How you do that is very, very open to your preference. Typically, it's a matrix with information entered in horizontal rows. Could very easily be a matrix with information entered in vertical rows if you choose. There's a number of good examples on the internet. Perry Johnson has some good examples on their website. So look those things over. and decide on a format you want to use and be consistent, because it really gets confusing if you do multiple types of calibrations or tests and you have multiple presentations of how you do measurement uncertainty analysis. The budget is typically the process of identifying uncertainty components or contributors, quantifying those components, in other words, putting numbers to how much they contribute, combining those components, then expanding those components and getting ultimately an expanded measurement uncertainty. The laboratory must define the manner in which uncertainty is accounted for when making statements of compliance with specifications. This was a requirement in the previous version. It is now embedded in what's called a decision rule in the new standard. And it is referred to in the new standard as a decision rule. Uncertainty for calibrations performed and CMC as it appears on the scope of accreditation must be estimated by the same method. That's a PJLA requirement, but it comes from an ILAC requirement, which was found in PL4. Bear in mind, ILAC rarely interacts directly with individual laboratories. They interact with accrediting bodies, imposing on the accrediting body a set of requirements. The accrediting body imposes those requirements uniformly, consistently on all the laboratories they accredit. Okay, what is measurement uncertainty? What are the sources of measurement uncertainty? Limitations in data defining a measurement is one source for uncertainty. Limitations in the capability of the measuring equipment is another source of uncertainty. Accounting for measurement uncertainty when making statements of conformity. Let's take a look at this topic. Measurement uncertainty calculation development. Uncertainty requirements related to calibration laboratories. Measurement uncertainty requirements related to testing laboratories. Bear in mind, again, they're different. Calibration is always treated in a particular way with respect to estimating uncertainty. The contributors may be different, there may be more or less of them, but the manner in which uncertainty is estimated is consistent, and it is required for every calibration performed. Measurement uncertainty requirements related to testing laboratories, some of them will look identical to those for a calibration laboratory, and they will be. Some, it will not even be necessary to perform the estimate because the development of the method included in the acceptance criteria the uncertainty of results. We'll talk about that a little bit later as well. We'll review examples of measurement uncertainty estimation for calibration and testing laboratories. Measurement uncertainty is, by definition, the extent to which a measurement result may differ from the actual or true value of the parameter being measured. Measurement uncertainty is not a measurement error. Keep that in mind, it is not a measurement error. And people used to talk about the uncertainty as the error in the measurement. And you were permitted to have no more than a particular amount of error in your measurements, or it would be out of specification. It typically does not occur in conversation with metrologists anymore because technically it's not correct. It's not an error in the measurement. Measurement uncertainty tends to result from limitations of the measurement and test equipment and lack of detail and clarity in defining the measurement and measurement process. Now, when we say lack of detail and clarity, it doesn't mean that there is no detail and that there is no clarity whatsoever. It means that it's limited. All the detail is provided is all there is. If it's very much, that's fine. If it's not a whole lot, that's just the way it is. And if there is some lack of clarity, that's unfortunate, but it doesn't mean that it isn't clear enough and detailed enough that you can use the method to perform the analysis. But keep in mind, measurement uncertainty tends to result from the limitations of the equipment and is not an error in measurement. A measurement result may be affected by both random variation and systematic variation in the measurement system. Random variation results in measurement uncertainty. Systematic variation typically results in measurement bias, which affects compliance with specification. Again, random variation results in measurement uncertainty. In other words, it causes measurements to deviate from what we expect the result to be. Of course, systematic variation typically results in the fact that the average of all measurements we take, no matter how many we take, deviates from the expected value by some fairly constant amount. We'll look at that graphically too. A random variation in a measurement process produces variation between individual measured values. It's the primary reason why if you measure something with a micrometer multiple times, you rarely repeat the exact same value for a reported result, especially as a micrometer has more and more resolution out to 6 decimal places. For instance, you will see it will be practically impossible to repeat the same number no matter how many measurements you take. Systematic variation, on the other hand, in the measurement process produces bias between an expected value and a measured value. Let's look at these two graphs. In both cases, the standard deviations are the same. So the width of the curves and the dispersion of data within the distribution is constant. The means, however, are different. You'll notice the one on the left-hand side, the bias is the difference between nominal or expected value and the actual result. A fairly large bias, it causes the curve to be shifted to where the green line on the top is above the red line on the top. So it exceeds the specification on the high side. Now, if you look at the same curve on the right, but it has a smaller bias, the actual result is closer to the nominal result. Now here, if you got the result on the left in your first measurements or your first analysis, it would be possible, perhaps, if it's a piece of equipment that's adjustable, you could adjust to where the bias is less, producing the condition shown in the lower right corner, which has the green lines within the red lines, the green lines representing the boundary of the 95% confidence interval, and that's within the specification limit. So you could say that this is within specification with a 95% confidence level. It's actually a little better than that. So systematic variation in the measurement process produces the bias. Systematic variation, oftentimes on adjustable equipment, can be eliminated or minimized, reduced. Bringing a piece of equipment that was outside of specification back into specification. Dispersion results from random variation. Now, random variation is random because we don't know what it is or where it comes from. There isn't anything we can specifically identify and fix or eliminate to remove random variation. It's kind of, you can think of it as the variation that is remaining after all identifiable sources of variation have been addressed. On the other hand, the bias results from systematic variation. Good example of this, I was using my wife's yardstick some years ago in the construction of the frame for my car, and I broke the end off of it. So I cut it off square at a convenient point at 35 inches. I neglected to tell her this though, so the first time she laid it out and cut a piece of material a yard long, it was short by an inch, and I had some explaining to do. But that would be a bias of systematic variation built into that piece of measuring equipment. And that, in that instance, it was not adjustable. So the bias couldn't be eliminated, had to be replaced, obviously. Okay, both distributions shown below in this example will have the same mean, but different standard deviations. The previous one, we had the same standard deviation, but different means. So let's take a look at the other situation. Both are fully defined by their mean and standard deviation, which is true for normal distributions. But you'll notice the curve on the left is fairly narrow. The mean, represented by the Greek letter mu, is midway between the upper and lower spec limits. In other words, it's right on the expected result. The green lines representing the 95% confidence interval are well within the red lines, which are the specification limits. So we would say, okay, this one's in specification. In fact, it's a specification with a greater than 95% confidence, greater than the 95% confidence interval. In other words, it could have more dispersion and still be within the spec limits up to a point. Now, the lower right-hand corner we have a curve that's much wider. The green lines representing the 95% confidence interval well exceed high and low the specification limits, although the distribution is centered. So this one we would have to say that we cannot say that it's in spec with a 95% confidence interval. Now this would be a case where there is no bias. So systematic variation is very small. There's always going to be some, but this is small enough that it's not detectable at the precision with which we were plotting data. Results have relatively small variation in the lower left corner. Results have relatively large variation in the lower right corner. And again, both of these have the same mean, different standard deviations. All right, quiz 3. When performing system analysis, there are two common types of variation, random and systematic. Which one is responsible for the dispersion of uncertainty values? This is question 1. The poll is now open. So select between the two. Okay, let's close the poll and we'll take a look at the correct answer for this one. All right, this one is random. Random variation is responsible for the dispersion of uncertainty values. In instances where you have large variation, you have large dispersion, large standard deviation. Small random variation produces tightly grouped data, relatively small dispersion, small standard deviation. Okay, next question. Which one, random or systematic, is responsible for the bias of uncertainty values? The poll is open. Let's make a choice on this one. Okay, let's close the poll and take a look at the correct answer. Systematic. The choice is number 2, systematic. Which one is responsible for the bias of uncertainty values? Systematic variation. Again, a yardstick that is 35 inches long would produce a bias in measurements. It would always be wrong in terms of length by an inch. It would be consistent, but it would be wrong in terms of the result would not be the expected result. It might still be within specification. Consequently, it might not be necessary to take any action to try to correct it or adjust it. Okay, let's look at the next question. Which type has the potential to reduce the risk of false acceptance and improve compliance with specification? All right, let's open the poll. Give you just a little bit of time to make a selection between the two. Okay, let's close the poll and we'll look at the correct answer. This also was number 2, systematic. And it's systematic because if you correct or adjust the bias, you will bring the results closer to being within specification. In fact, in the example we looked at, it came completely within specification by reducing the bias. Laboratories can choose if their equipment is within specification but has a rather large bias, that means they can still use it. It's still within specification, still satisfies the 95% requirement in that regard. Most laboratories, though, want to adjust it back as close to mean as possible, and that improves even more the extent to which it's within spec, which means that it can tolerate some displacement. Electronic equipment tends to age over time. Even if it's not used much, it changes just with the passage of time. Laboratories that calibrate the same piece of equipment on a frequent basis, every 6 months or every year, over time they can detect a visible trend in the aging, and they can make predictions about when it will no longer be in specification. They can use that information to either make adjustments and always bring it back to mean or as close to mean as possible, or they can use that information to justify extending the period between calibrations because of the stability of the instrument. And then they would augment that with intermediate checks where they're taking a look at a point in time to how the instrument is performing to ensure that it's still behaving in the same way and that the trend line that they observed is still true for the data that they have. All right, now we want to look at some examples of machine and test equipment limitations. Limited resolution. Resolution may range from very fine, that would be an instrument that can resolve or discriminate between items with very small differences. An example would be a micrometer with a 0.025 millimeter resolution. Then to very coarse would be an instrument that can only resolve or discriminate between items with relatively large differences. Let's go back to my wife's yardstick with a 3 millimeter resolution. So that would be a coarse resolution compared to the micrometer, which has a fine resolution. So resolution is one of the limiting factors to consider in uncertainty of measurement equipment. The instrument and the unit under test both expand beyond their calibrated length due to temperature exceeding the standard temperature of 20 degrees C. This means laboratories engaged in either dimensional calibration or dimensional inspection must work to control their temperature and keep it to the degree possible, keep it at 20 degrees C, or certainly establish a small plus and minus tolerance to that. Low relative humidity and non-standard temperature might result in accelerated evaporation of distilled water used to calibrate a pipette. So in certain laboratories, control of relative humidity would be critical, just as control of temperature is critical in a dimensional laboratory. The weight of a precision mass must be adjusted based on the local value of G where it will be used compared to the local value of G at the location of calibration. In other words, the attraction due to gravity, the acceleration due to gravity is dependent on the location. And it changes from location to location based on elevation above sea level, which is farther displacement from the center of gravity, the center of the Earth. Also, in particular areas where the Earth material below your feet is more dense than in other places, that can affect it also because the denser material would increase the value of G. So typically when you have mass calibrated, the people performing the calibration need to know the value of G at your location, and they adjust the weight so it will display the correct weight at your location, even though it will not at theirs because G is different. So these are some of the measurement and test equipment limitations. It's just a small example. There are many, but this hopefully gets you in tune of thinking of what might be changing and what might be the magnitude of those changes of all aspects of a measurement or calibration process. Let's look at some additional limitations. The test procedure defines the manner by which the test is to be performed. In other words, you might be able to accomplish a test by a variety of different means, but for repeatability purposes and compliance with a method purposes, you must perform it the same way every time, consistent performance, and that's one of the things that's evaluated during assessment. Where time is critical to the outcome of the test result, resolution of the timing device affects the extent to which the result is uncertain. In other words, you wouldn't want to be taking measurements that have to be within plus or minus 2 seconds and use an hourglass to measure the time, or a sundial. You'd want something that measures to a pretty high level of precision. Digital wristwatch would be adequate in most cases. Precision timing devices are relatively cheap, and most laboratories that need to have a low resolution device can do so at a small cost. The dimensional definition of an apparatus for performing the test has liberal tolerances, which may result in relatively large variation between otherwise similar pieces of equipment. Now, this might be an example like the two graphs we looked at that had similar had actually equal standard deviations or measures of dispersion, but had different means. And a different, one machine might have one particular mean or amount of systematic variation because of the way it was assembled. Holes have a 32nd of an inch clearance for a bolt, or have 0.75 millimeters clearance. And in one machine, it's shifted all the way to the left, and the next one, it's shifted all the way to the right. Both of them are acceptable and within specification for the equipment. But those are the kind of things that would produce systematic variation showing up as a bias in the readings. In some instances, published test procedures contain the acceptance criteria and describe the sampling method by which they were determined. The method was statistical, but important statistical parameters are not clearly stated or defined. In other words, they tell you we performed a large series of tests involving a large number of laboratories and personnel and pieces of similar test equipment, but they don't tell you the statistics. They simply say, here's the acceptance criteria. They were developed in this method. And that's fine. That's suitable. But just bear in mind that although in their analysis of the data, in order to produce the acceptance criteria, they used statistics and basically did a type A analysis. To you, it's type B because you simply get it from the published value. Okay, let's talk a little bit about accounting for measurement uncertainty for making statements of compliance. Very important. Again, this is taken verbatim from the standard 7.8.6.1. When a statement of conformity to a specification or standard is provided, the laboratory shall document the decision rule employed, taking into account the level of risk, such as false accept and false reject, and statistical assumptions associated with the decision rule employed, and apply the decision rule. So this is an effort to pin down specifically what the writers of the standard, the authors, wanted to see happen when accounting for measurement uncertainty, making a statement of compliance. The decision rule must be mutually agreed to and documented. In other words, this isn't something that the laboratory says, this is what we do, and do it. It has to be something that is agreed to by both parties, the customer and the laboratory, and the time for that to happen would be in the review of requests, tenders, and contracts. A laboratory might decide, we can't do that. We can't live with that. If you have to have that particular decision rule, we have to decline the work. That's fine. What they can't do is they can't say, no, we're not going to do that. This is what we do. It has to be agreeable to both parties. And as usual, the customer gets what he wants. If the customer says, I know that's how you normally do it, but this is what we want. Either the laboratory agrees to do that and then does so, applies that decision rule in making the decision, or they decline the work. False acceptance and other types of risk must be taken into account along with statistical assumptions. False accept, for instance, if you have a 95% confidence level for the uncertainty, and that establishes the confidence interval, if that confidence interval is contained within the specification limits, even if just barely, then you have at least a 95% likelihood that the results really are within spec, and you have a 5% likelihood that they're not. That 5% likelihood they're not is the risk of false acceptance. If the laboratory was to take it, it's taking a risk that 5% of the measurements for that equipment will be wrong. But it's 95% risk that they're not. And so that's a reasonable ratio. It's a reasonable level of false acceptance risk. And it is produced in what has always, or for the most part, been acceptable to laboratories, and that's the 95% confidence interval being within specification. That's how we used to talk about it. Now in the new version of the standard, they want us to consider that as false acceptance risk, which it is. It's perfectly fine to do so. The decision rule must be applied in making the compliance statement. In other words, you develop the mutually agreed to decision rule, then you get a measurement result and the estimated uncertainty that is determined whether it is or is not within specification. Let's look at an example of a decision rule in a compliance statement. A valid decision rule would maybe look as follows. A test result will be considered as in compliance if the risk of false acceptance does not exceed 5% with the uncertainty estimated at an approximate 95% confidence level with K equals 2. Now, the expression of the confidence level and the value of K is a requirement that comes from ILAC P14. So technically, if you say that it's within 5% risk of false acceptance, and if that's true, you don't have to know what the confidence level was or the K value in order to determine that. If the laboratory estimates the risk of false acceptance and tells you it's within 5%, then that's fine. But ILAC P14 requires that the confidence level and the value of K be published on the certificate. Corresponding and valid compliance statement is as follows. The false acceptance risk associated with the test results is 4.2% and is considered to be in compliance based on the decision rule agreed to and stated on this test report. Now, it could be a calibration certificate just as easily. Application of the decision rule would require that the risk of false acceptance be calculated, and if it is not greater than 5%, the results are stated as being in compliance. So that's, you have a decision rule, you have a compliance statement. The way you arrived at the compliance statement was by application of the decision rule to the results and the uncertainty. If, on the other hand, the risk of false acceptance exceeds 5%, the result is stated as being in non-compliance. In other words, you at that point cannot say that it's within specification with a 95% confidence interval. All right, question 4. What is the decision rule? It's a rule used by both parties to determine if the measurement uncertainty has been properly estimated and applied to the results. It is a rule agreed to by the customer in the laboratory defining how uncertainty is accounted for when making a statement of compliance with a specification. Number 3, it is a rule recommended by the calibration service provider, and acceptance by the customer is mandatory in order to establish traceability of the calibration results. All right, let's look at the poll and make a selection. We'll give you a little bit of time again for this. Okay, let's close the poll and look at the correct answer. What is a decision rule? It is a rule agreed to by the customer and the laboratory defining how uncertainty is accounted for when making a statement of compliance with a specification. And I stuck this in, this is additional, this wasn't part of the question, but uncertainty is applied to the measurement result according to the decision rule, and the compliance decision is made on that basis. Here's where this is found, 7.8.6.1. When a statement of conformity to a specification or standard is provided, the laboratory shall document the decision rule employed, taking into account the level of risk, such as false accept and false reject, and statistical assumptions associated with the decision rule employed, and apply the decision rule. So this is where the correct answer is found, verbatim from the standard. Just keep in mind the decision rule is the instructions telling you how to make the decision about compliance, applying the uncertainty to the measurement result. Okay, we're going to stop here, take about a 15-minute break. Let's see, it is right now 9:04, so be sure that you're back at 9:19, and we'll start the second half. You can take this time if you want to perhaps document some questions, or be prepared to document those so we can answer them at the end of the second hour. Thank you. Okay, that's close enough on the 15 minutes, so let's get back to our presentation. We want to talk first about measurement uncertainty included in a test method. This is, again, one of the things that's unique about testing is oftentimes the nature of the test is such that acceptance criteria have been developed for the test, and the manner in which the acceptance criteria was developed included the uncertainty resulting from the test results obtained in developing the method. Typically, the method would have involved a large number of laboratories performing a large number of tests, so a lot of data. And 30, when you're doing statistical analysis, if you have 30 values, that's considered a statistically significant sample. And you may hear that again later in the presentation. So most of these tests that are developed that are intended to include the uncertainty in the results are plus or minus 3 sigma standard distributions, normal distributions of data, and they generate results that should be applicable for all laboratories, potentially all laboratories in the world. If the test is done, if data is collected on a worldwide basis to develop the acceptance criteria, then all laboratories within the world should be able to use that method, follow the method explicitly, as we'll talk about, and get an acceptable result, a result within those limits. And the result within those limits is typically intended to represent a 95% confidence interval. We'll talk about that a little bit further as we go. So in particular, I'd like to, at this point, talk about the ASTM D6184-98, standard test method for oil separation from lubricating grease using the conical sieve method. Very specific test, very specific equipment to be used. Let's take a look at compliance of test results with performance specification. Repeatability. Now they define, in this standard, they define repeatability and they define reproducibility. So pay attention to these definitions. Repeatability is defined as the difference between two test results obtained by the same operator with the same apparatus under constant specified operating conditions on identical test material would, in the long run, in the normal and correct operation of the test method, exceed the following values only one case in 20. So then they give you a value that as long as you do not exceed that, then you should have an acceptable result 19 times out of 20. Let me restate that. 19 times out of 20. Reproducibility. Now this is defined as the difference between two single and independent results by two different operators working in different laboratories on identical test material would, in the long run, in the normal and correct operation of the test method, exceed the following values only one case in 20. And again, you have a published value, acceptance criteria, and if your result is within those limits, you should have, it should really be an acceptable result 19 times out of 20. In both cases, M is the mean of two tests or determinations. What does this mean? The way it's stated, what does it mean? Well, let's look at what it means. It means a trained laboratory technician performing the test in accordance with the prescribed method, in other words, consistently following the procedure, under the prescribed conditions, in other words, environmental conditions such as temperature, barometric pressure, local value of G, etc., are within acceptable limits. The test would have to specify what those limits are, and the affected environmental conditions would have to be within the stated limits. Now, they might be just barely in, or they may be in dramatically. And one's going to give you a test that's got a much more certain outcome, and the other is going to be not as good, but still within the acceptable limits based on a 95% confidence interval. Using specified equipment, in other words, not substituting equipment which may perform differently than the equipment specified. I was in a laboratory that used a piece of equipment designed initially and developed by a professor at Ohio State University. So it is referred to in industry as the OSU, go Bucks, the OSU test. So it's very specific. They can't perform that test and be part of this group that's using that to get acceptable results if they substitute a different piece of equipment. So it requires that you're using the prescribed equipment in the correct manner, using the prescribed method and so forth, but not substituting equipment which may perform differently. Let me back up just a second when I ask it. Well, I'll ask a question, and in answering it, I will, you can't visually or verbally answer it, so I will. Using or not substituting equipment which may perform differently than the equipment specified. Now, every one of these OSU machines, the Ohio State University test machine, every one of those will perform slightly different than every other one, and that is the systematic or the random variation that results from just the nature of manufacturing. Its systematic variation may produce some difference in the readings because it may give a larger or smaller bias, or the bias might be negative instead of positive, as it was in our examples, and so forth. So those kinds of variations are one thing, but they can't take a totally different piece of material with different operating theory and different mechanisms and so forth, and attempt to enter that in with a group of similar machines to one another, the OSU machines that are collecting the data, performing tests, and evaluating against developed acceptance criteria. Okay, so under those conditions, the laboratory can evaluate its results against the stated acceptance criteria and can then report acceptance or rejection against the stated acceptance criteria with a 95% confidence level. In other words, 95% is what we work with most commonly in metrology. But when the test says that you can expect to get the right result 19 times out of 20, 1920 is 95%. So it's exactly the result that we're accustomed to working with when we're working with a 95% confidence level. Okay, question number 5. Are the following definitions of repeatability and reproducibility correct? Repeatability, multiple tests performed by the same operator using the same equipment. All right, let's turn on the poll and we'll look for a response to this. Multiple tests performed by the same operator using the same equipment. Is that the definition for repeatability? All right, let's turn off the poll and look at the right answer. I'm sorry, we should have looked at both of them. Let me back up a minute and we'll turn the poll back on. Can we turn the poll on? Okay, answer the second one too. Is that correct? Okay. Are they correct? Yes, they are. Repeatability, multiple tests performed by same operator using the same equipment. Typically, this reveals the results of random variation. Reproducibility, multiple tests performed by 2 different operators in different laboratories. Typically reveals the results of systematic variation. And again, this was found, these definitions were found in this specific ASTM D6184-98 test method. It's found on page 3 of 4 of that standard. It's always important to be able to reference back to where you found information that you're using as a basis to perform analysis. Okay, acceptance criteria are developed by in-depth statistical analysis of sample results from multiple laboratories performing the same test multiple times. Typically, large number of laboratories and large number of times they repeat the test. And by large, I'm saying probably at least 30. Sample data obtained from multiple laboratories performing the same test multiple times permits the determination of the mean. That's what that it looks like a lowercase m. It's called mu in the Greek alphabet, That's used to represent the mean. So the determination of the mean of the distribution of sample averages. The experimental standard deviation of the mean. That's the mean of the distribution of sample averages. Not terribly important that you remember this because you can find it, okay? And the standard deviation. This is used to establish acceptance criteria with a probability of 19 out of 20 or 95%. Uncertainty is present due to variation of equipment, operator skill, and reproducibility, but the manner by which the acceptance criteria is determined includes the uncertainty in the method of the analysis and therefore does not require further analysis of uncertainty. If you're working with a test method that gives you acceptance criteria and tells you it's based on this kind of a development, then the uncertainty is considered as being part of the test acceptance criteria, and you don't have to do a separate estimate of the uncertainty. All right, let's look at the summary of test method 4.1. The weighed sample. Now this is the oil separation from grease using a conical sieve method. The weighed sample is placed in a cone-shaped wire cloth sieve suspended in a beaker, then heated under static conditions for the specified time and temperature. I know there's a misspelling there. Unless otherwise required by the grease specification, the sample is tested at standard conditions of 100 degrees centigrade, Celsius, plus or minus 0.5 degrees Celsius for 30 plus or minus 0.25 hours. The separated oil is weighed and reported as a percentage of the mass of the starting test sample. The sample is weighed on a balance. Makes sense so far. It is heated to a specified temperature. It is maintained at that specified temperature for a specified time. The sample is visually examined to detect non-homogeneity, such as oil separation, phase changes, or gross contamination. Detailed dimensions with tolerances are provided for the cone and the wire mesh material of which it is constructed so that they can be essentially similar from machine to machine, test to test. A target dimension is provided to ensure that the amount of sample material in the sieve is approximately the same for each test. Sample is visually examined to detect non-homogeneity, such as oil separation, phase change, gross contamination. The balance must have a 250 gram capacity with 0.01 gram resolution, fairly small resolution. The sample is heated to 100 degrees C plus or minus 0.5 degrees C. Sample is maintained at the specified temperature for 30 hours plus or minus 15 minutes, 15 minutes being a quarter of an hour. These potential variations were present during the statistical analysis which developed the acceptance criteria. As a result, further evaluation of measurement uncertainty is not required. All right, now we want to talk about developing an uncertainty budget for micrometer calibration. Much of what we're going to look at here would be applicable to a budget for uncertainty from a test as well. So pay attention as we go along. Keep this for reference too. It's recorded and will be available for download from the Perry-Johnson website, as we told you earlier. So it'll be good reference material. But let's proceed. A micrometer calibration typically has 6 significant sources of uncertainty. Now remember, there are many others, but we applied a test for significance and eliminated all but these 6. And the test that we use states that if one contributor by itself or if several contributors taken together do not contribute more than 1% of the total, they can be set aside as insignificant. So from that point going forward, we would only evaluate the 6 remaining significant contributors. And we're going to take a look at each one of those and talk a little bit about where it comes from, what causes it, how to evaluate it, how to assign value to it, and then how to process it in an uncertainty budget to ultimately wind up with a number referred to as the expanded uncertainty. The very first source that we want to consider is the uncertainty of the standard used to calibrate the micrometer. Then we want to look at uncertainty due to non-repeatability. Now remember, you may see this term as repeatability, the uncertainty of repeatability. It's actually the uncertainty of the non-repeatability or inability of the device to repeat a reading. Uncertainty due to limited resolution. We talked some about what that resolution might be. We're looking here with a micrometer to have a fairly small resolution, which means it can discriminate between very small differences on two different items. So if you took two supposedly identical components and wanted to measure a dimension on them, the micrometer has to have enough resolution that it can detect a difference in size between the two within the specification for that dimension. All right, number 4, uncertainty due to non-standard temperature. Temperature is a big deal in dimensional calibration laboratories. It's often said that the laboratory with the best thermometer wins because so much of it is temperature related. Uncertainty of the temperature measurement device. Here's another temperature sensitive contributor. The temperature of calibration is being measured with a temperature device, which itself has to be calibrated, and as a result, it has its own uncertainty associated with its calibration. So just like the standard that we use has calibration uncertainty, the temperature measurement device does as well. And then the last one is uncertainty due to differential temperature. And what this is accepting the fact that as the temperature fluctuates within the laboratory, typically between plus and minus 1 or plus and minus 2 degrees, depending on what the laboratory has established, that as it fluctuates between those two, items that have very small mass are going to respond to the temperature change more rapidly than something that has a lot of mass. For instance, a surface plate is not going to respond as rapidly to a temperature change as a thread wire gauge pin would, which would be maybe 40 or 50 thousandths, 1 millimeter or slightly more in diameter, depending on pitch of the thread it's used for. So recognizing that the temperature is constantly fluctuating between the acceptable limits and everything in the laboratory is responding to those temperature changes, we can't measure that on an instantaneous basis. So what we do is we make an educated assumption of what it might be. We evaluate the linear coefficient of thermal expansion for the material that the micrometer is made from, the same for the material that the gauge block or whatever we're using as a standard is made from. Recognize with the micrometer that it might be made of several different kinds of material. There may be steel, there may be some aluminum or some other kinds of material that go into it, but we're going to kind of arrive at a decision that we're going to say the majority of it is this material, so we're going to treat it as if it's all that material for purposes of thermal expansion. This is an interesting study, and hopefully you'll learn some things here that you can apply across the board, but let's proceed. Here's quiz number 6. When preparing an uncertainty estimate of test or calibration results, where is the uncertainty of the standard or standards found? On the purchase order for calibration services, on the invoice for the unique calibration performed, on the calibration certificate or test report. The customer is responsible for estimating the uncertainty based on their specification. Okay, the poll is open. I'll give you about a minute or so. It's a lot of verbiage to consider, but it shouldn't take too long. Okay, let's go ahead and close the poll and take a look at the correct answer. Number 3, on the calibration certificate or test report. So when I take out a gauge block that's going to be used in the calibration of this micrometer. In other words, I'm going to use the micrometer to measure the gauge block. I know the size of the gauge block because I had it calibrated, and I know its size within the limits of its uncertainty. And I expect the micrometer to tell me that same result. So the place I go to get that uncertainty from the calibration of the standard is the calibration certificate or test report. That was number 3. The source, and again, this is right out of the standard, the measurement uncertainty of the measurement result. This is in the section of the standard is talking about reporting results. What has to be on a calibration result? The measurement uncertainty of the measurement result. Now, I told you that in the 2005 version, it had to be on the report unless a statement of compliance was made. And on the if a statement of compliance was made in the 2005 version of the standard, then whether you put the uncertainty on the certificate or whether you didn't was optional, because it had already been determined and it had already been used by the laboratory, applying it to the result to evaluate compliance with specification. There was then the caveat based on ILAC P14 that if the equipment calibrated would be used in itself to perform calibrations, then it had to be on the certificate. They've taken care of that issue in the 2017 version of the standard by saying, regardless, the measurement uncertainty always has to be on the certificate, always. So as you're operating under the new standard and preparing test reports or calibration reports, test reports where you had to estimate the uncertainty, it didn't apply if the uncertainty is factored into the acceptance criteria. But if the uncertainty has to be estimated for a test result, and it always has to be estimated for a calibration result, in both cases, it would have to be on the calibration certificate or the test report, regardless of how that particular instrument was going to be used. So it always has to be on the calibration certificate. It will have to be on the test report unless the uncertainty is inherent in the method and procedure. Okay, a calibration certificate should also include a couple of other pieces of necessary information. It should include the confidence interval, typically 95%, and the coverage factor, typically 2. The source for that, again, is ILAC P14. We've mentioned it before, but it doesn't hurt to mention it again. And the decision rule, if a statement of compliance has been requested. That comes from 17025, 7.1.3 for the use of the decision rule. The decision rule shall be clearly defined on the calibration certificate. Additional requirements for calibration certificates are found in sections 7.8.1, 7.8.2, and 7.8.4. However, not all of these are used in making a compliance statement, so I didn't reproduce them on this slide. Now you'll notice that 7.8.3 is not included there. Very good reason for that. 7.8.3 are reporting instructions unique to test laboratories, In other words, they have no application for calibration laboratories. They do apply to every test laboratory. On the other hand, then 7.8.4 is unique to calibration certificates and calibration laboratories. Has no application at all for testing laboratories. It's mandatory requirements for calibration certificates. And be aware of the distinction. Those things which are required in 7.8.3 for testing laboratories do not apply to 7.8.4 and vice versa. Okay, let's look at some given information for this calibration. The uncertainty of the standard is 0.278 micrometers with K equals 2. The uncertainty due to non-repeatability. We're going to take 5 sample readings and take the average. Remember, two things that we said, that the average of multiple readings is the best indicator of the true value. And the reason that we take 5 readings and all of them are slightly different is because of random variation, primarily in the measurement device. It's the measure of the limitations of the measurement device for sure. So we take 5 sample results, and here they are. We find the average of those 5 results. We find the standard deviation of those 5 results. From that, there's a formula that allows us to calculate the experimental standard deviation of the mean and we have that here. So we have the piece of information that is necessary for us to know the uncertainty due to non-repeatability and proceed the analysis from there. All right. Number 3, the uncertainty due to limited resolution. Now, let me pause here, and I want to say every one of these contributors comes from some form of statistical distribution. When we're talking about the uncertainty of the standard, and we get that value from a calibration certificate, it is the result of a normal distribution, and in most cases, it's going to be k equals 2, which means that it's plus and minus 2 standard deviations. And plus and minus 2 standard deviations will be the amount of the distribution captured between plus and minus 2 sigma of a normal distribution. All right, moving along. Resolution of the micrometer is piece of given information, 2.50 micrometers. The distribution for resolution is what's called a rectangular distribution, typically referred that way as by metrologists, but pure statisticians would refer to it as a uniform distribution. And we'll be looking at the different types of distributions we encounter primarily in doing uncertainty analysis. So suffice it to say at this point that we have the resolution of 2.5 micrometers, and from that we can find the standard uncertainty, and we will. The uncertainty due to non-standard temperature. The calibration was performed at 19 degrees C. For scientific and technical purposes, 20 degrees C is considered standard temperature. If you report dimensional values, size of a gauge block, size of a gauge pin, whatever, at any temperature other than 20 degrees C, it's necessary to calculate the variation due to the coefficient of thermal expansion and correct the result as a result. You either have to report the temperature at which you perform the calibration so the user can correct it for temperature, or you have to make the correction and report that as the result. We'll talk further about thermal coefficient of expansion. 12 micrometers per meter per degree C for the material that we're looking at here, the steel of the micrometer and the steel of the gauge block. Here's a formula that allows us to calculate what I refer to as the effective coefficient of thermal expansion. In other words, if we have 2 items that have different coefficients of expansion, let me say this too. The coefficient of thermal expansion itself typically is uncertain by plus or minus 15%. Some materials that might only be 12%, some may be 17%, but it's typically considered as a 15% plus or minus uncertainty in the rate of expansion. So if we say that it should expand 12 micrometers per meter per degree C, that is plus or minus 15%. So if you take, in this equation, if you take 12 and multiply it by 1.075, we're increasing the size by 0.75%, and then we subtract from that 12 times 0.925, which is 1 decreased by, again, 7.5%. The absolute value of that calculation is the effective coefficient of thermal expansion. Now, if these materials had different coefficients of expansion, we would put them in. For instance, if the gauge block was ceramic material and expanded at the rate of 8 micrometers per meter per degree C, then we would put in 8 times 1.075 minus 12 times 0.925, and again calculate an effective coefficient of thermal expansion. The formula will tell you, if you work with it, you will find that if that device, which has the largest coefficient, increases in size, and that device with the smallest coefficient shrinks in size, that gives you the greatest separation between the two. On the other hand, if the one with larger coefficient of thermal expansion got 15% smaller or some percentage smaller, and the one with the smallest coefficient expanded, they would move closer together. They would come closer to having the same exact coefficient of thermal expansion. So is it always, is the 15% going to occur? Nah, not always. It will be an extreme. The worst it will be is plus or minus 15%. However, is it not going to occur? Is it going to get bigger? Maybe some of the time it's plus 15%, some of the time it's minus 15%. The point is, the extreme condition of being 15% plus on one and 15% minus on the other is not likely to occur. But also zero is not likely to occur. So we choose to say, and you could choose something different, but I think you'll see the logic of this. Instead of plus or minus 15%, we're saying that rather than expect that the extreme condition is going to happen, we're going to say that it's more likely that a medium point occurs. And so we work with plus or minus 15% all the time, rather than work with plus or minus 15% always, when it's not likely to occur. So instead of using 15%, we're going to use 7.5% and say that they might grow or shrink by that amount. And that's what this equation does. It's using 1 plus 7.5% is the first term, and 1 minus 0.75% is the second term. And it gives us an effective coefficient of thermal expansion of 1.8 micrometers per meter per degree C. The uncertainty of the temperature measurement device. Now, where does this come from again? It comes from the calibration certificate for the temperature measurement device. We found it to be 0.39 degrees C with K equals 2. Uncertainty due to differential temperature. This is something, again, you have to make a reasoned approximation of what makes sense. You have to first off recognize what differential temperature is, why it occurs, what's it likely to be. If you control temperature in your laboratory to plus or minus 1 degree C, then a value for a differential temperature, how much is the temperature different between a small mass item and a large mass item? 0.25 degrees C may be reasonable. If you control the temperature to a larger number, for instance, plus or minus 3, well, then maybe plus or minus 0.5 degrees C would be a better number. Just arrive at it by a reasonable analysis of temperature conditions and comparative ratio of mass of one to mass of the other, and come up with a number that you then apply all the time. Be prepared to defend it. So if you do some study and you look at what would the maximum displacement be, what's the minimum going to be, and what are you going to use, I would just advise you to write that down, document it, and keep it on hand, because if an assessor ever says, well, where do you come up with this, you can defend your choice. Most assessors are not going to say, well, 0.25 is way too small or 0.25 is way too large. They're simply going to be looking for the fact that you have a value and that it makes sense. And it makes sense on the basis of defending it with the documentation you retain. All right, let's look at the uncertainty of the standard and how we're going to process it. It's found on the calibration certificate. It results from a type B analysis because we didn't do it statistically. Now, the laboratory that calibrated it may have been type A analysis for them because they did use statistics to arrive at it. But they give it to us as part of a document. It's printed information, therefore it's a type B analysis. And to be honest with you, type A, type B is just record keeping and helps us to remember and understand how the calibration took place. It does not change the value of the numbers. All right, the D of F, this is degrees of freedom. It's a measure of how much information do we have or do we know. And remember I told you earlier that 30 is a statistically significant sample. We're going to use this number here. Technically, items that are arrived at by type B analysis do not have any associated degrees of freedom. On the other hand, items that are arrived at, or their uncertainty is arrived at by type A analysis, applying statistics, they have degrees of freedom. For instance, if we measure 5 items, as we did, and take the average of those, the degrees of freedom is the number of samples minus 1. So in our case, we did 5 samples. It'd be n minus 1, with n being 5. Degrees of freedom would be 4. We use this because there is another term we're going to encounter later in the analysis, and it's called the Welch-Sater weight equation. and it allows you to calculate effective degrees of freedom for values obtained by type B analysis. Some people would argue that it has limited importance in certain calibrations, highly significant in other calibrations. I would say that I tend to agree with that. I also would say, though, that if you're doing your budgets in an Excel spreadsheet, your ability to perform calculation, the time it takes to perform them, and it's not significant. It doesn't slow you down any. Once you build a budget and you include this calculation in it, it's there every time, and it's done literally at the speed of light, so it has no performance impact on you. So 30 is a significant statistical, significant sample size. Some people use 100, some people use 30. I saw it used to be that when these were done by hand, people would just put an infinity symbol in here as the number. Well, we can't have an equation in Excel where one of the terms is the infinity symbol. So I picked an arbitrarily larger than necessary number of 1,000, where I could have used 100, could have used 200, whatever. I just typically use 1,000 all the time. So when you see a degree of freedom of 1,000 for data arrived at by a type B analysis, know that it is for use in the well-stated weight equation, calculating effective degrees of freedom, and you don't have to remember much more about that at this point. The distribution type is normal. Now I note it as normal expanded because it is the standard deviation multiplied by a coverage factor to get an expanded uncertainty. Now, this is a good time to tell you that K is the standard deviation. When we're talking in metrology, we don't call it a standard deviation. We call it a coverage factor. But in reality, what it is plus and minus the number of standard deviations we have. The divisor is K. Typically, this is 2. Now, often in the pharmaceutical industry, they want to use a divisor of 3, K equals 3, so they can get a 99.73 probability. In other words, the confidence interval would be 99.73% enclosure of data as opposed to 95%. With a plus and minus 2 standard deviations. Typically, outside the pharmaceuticals, you're going to be working with K equals 2. If K is going to be equal to 3, that's a piece of information, again, that has to be determined at the review of requests, tenders, and contracts. Standard uncertainty is the uncertainty divided by K. So if we're told what the uncertainty of the standard is, and we're told what the coverage factor is, we divide the uncertainty by K, and we get the standard uncertainty or standard deviation of the uncertainty distribution. C of S, coefficient of sensitivity, is 1 since there are no correlations with other sources. Now, that in some respects is a judgment call that it's a person saying one of these contributors, if it changes, that does not necessitate a change in the other. On the other hand, if changing one forces another one to change, then they are correlated, and there's a way to deal with that. The variance is the standard uncertainty times the coefficient of sensitivity, that product squared. Now, let me back up just a minute and tell you what the other way to deal with this is. If there is a correlation, then you express it as both values as a function of one relative to the other. You extract the partial derivative. The other way, which is much simpler because most of us have not used calculus in recent years, some perhaps more recently than others, but most people want to avoid it if possible, and I recommend that because for those who are going to be looking at the document, they need to be able to decipher the mathematics that were used in developing it. And many customers may have no exposure whatsoever, or again, a long time since they've had any to calculus. So the alternative is numerical analysis. You look at a particular test point where this will be used and evaluate the effect of one contributor on the other where there is a correlation, and reduce it to a numerical analysis giving you a specific value rather than using partial derivatives, which tell you the relationship over time, employing the derivative. So in this estimate that we're performing, coefficient of sensitivity is 1 in all cases, so we don't have to deal with that. But we can talk about that. You may have questions during the question and answer period. The variance is, again, the standard uncertainty times the coefficient of sensitivity squared. Uncertainty due to non-repeatability. The experimental standard deviation of the mean determined from a sample of 5 measurements is the the standard deviation divided by the square root of the number of samples. So it would be the standard deviation, which we found, divided by the square root of the number of samples we took, which is 5. And that allows us to estimate the mean of the sampling distribution. I'm sorry, the standard deviation of the sampling distribution. I misspoke. I'm sorry. It results from a type A analysis. That was statistical. We applied some statistics and getting an average, from that calculating a standard deviation, and from that calculating the experimental standard deviation of the mean. The degrees of freedom, sample size, -1, n -1, and in this case, it's not arbitrary. I couldn't have chose something else. It's by definition n -1. So we have 5 samples, n is equal to 5, 5 minus 1 is 4. The distribution type is normal standard. You recall when we were talking about the uncertainty of the standard, it was normal expanded. Here, when you calculate the standard deviation, you're getting just that, the standard deviation, not 2 times the standard deviation or 3 times the standard deviation, but the standard deviation. So we don't have to divide this by anything to get to the standard deviation because it's what we already have. The divisor is K. Typically, this is 2. Standard uncertainty is the uncertainty divided by K. In this case, K is equal to 1, not 2. Coefficient of sensitivity is 1 since there are no correlations with other sources. And let me back up here a minute and explain why it isn't 2. And I made a point out of the fact that we estimated the standard deviation, 1 standard deviation. So we want the division in the equation so that it will work. If we put in a 0, or if we don't do a division, we don't get the terms related to the standard deviation, namely the variance. So we have to have the ability to divide by something. If we divide by 1, it doesn't change the value of the number at all. And in reality, it is divided by 1 because we have the standard deviation, 1 standard deviation, divided by 1 equals 1 standard deviation. So it doesn't change, it doesn't reduce it or make it larger. It carries it through the calculation, but it keeps it the same, which is exactly what we want. So where the divisor is typically K, in this instance, it's not. So it isn't, typically it might be 2. In this special case, where we're calculated the 1 standard deviation, it's 1. Again, there are no correlations, so the coefficient of sensitivity is 1. And the variance in all cases is going to be the standard uncertainty times the coefficient of sensitivity, and that product raised to the 2nd power. Uncertainty due to limited resolution. The half interval of the resolution is the resolution divided by 2. In this sample, the resolution is 2.5 micrometers. Therefore, the half interval is 1.25. So if the micrometer measured a particular value, the resolution is hidden from us. In other words, we can't know what it measured by any more than 1/2 of the resolution. Now we might measure multiple times, and it's actually detecting internally a difference of a billionth of a meter. However, we can't see that on the indication, the display or the output, because it only outputs to 2.5 micrometers. So we could say, well, it might be right in the middle of that. So it's some number plus 1.25 and minus 1.25 to give us the width of the interval. But we don't know beyond that what it is within that interval. And so we're talking about the half interval. You could choose to work with the entire interval or the half interval. And I'll tell you why this makes a difference in a little bit. Keep it in mind, though. So we've got the half interval of 1.25. Results from a type B analysis. There's no statistics involved. The degree of freedom is 1,000, and that, again, I told you before, is an arbitrary number. The distribution type is rectangular or uniform. Rectangular, when you're talking to metrologists, if someone calls it a uniform distribution, they're probably a statistician. The divisor, in previous cases, we had a divisor of 2, which is typical. We had a divisor of 1 because we had calculated exactly 1 standard deviation. Here, the divisor is the square root of 3, which is equal to 1.732, expressed at 3 decimal places. The standard uncertainty is the uncertainty divided by 1.732. Let's back up to that a minute because there's a point I want to make. Standard uncertainty, here we're using the half interval, so it's going to be half interval of 2.5, which is 1.25. So we would find what is the value of the number by taking 1.25 and dividing that by the square root of 3. If we worked with the whole interval instead of the half interval, we would use 2.5 divided by 2 times the square root of 3. You can work either way. Either one's fine. Either one will give you exactly the same answer, and that answer will be correct. But I would advise you to choose one method and use that all the time. Myself, I work with the half interval all the time. Just a matter of preference. I can't say that it's better than working with the full interval. It's just what I'm accustomed to. I would encourage you to adapt one and stay with it. And because a lot of published material is going to be working with the half interval, I think I would encourage you to do that. But again, the choice is yours. Just be aware of the difference. Again, coefficient of sensitivity is 1 since there are no correlations with other sources. Variance is, again, the standard uncertainty times the coefficient of sensitivity of that quantity squared, or that product squared. Now we're looking at uncertainty due to non-standard temperature. Standard temperature is typically 20 degrees C. The spreadsheet is programmed to calculate the dimensional effect of non-standard temperature. Another important point, when you're doing an estimate of uncertainty, you need to get all the terms converted to the same units. So we're not measuring in units of temperature, we're measuring in units of meters or millimeters. However, the temperature indicating device is outputting a number of degrees of temperature. So what we have to arrive at is what is the dimensional effect of a change in temperature. Results from, again, type B analysis. Degrees of freedom is 1,000. Distribution type is U-shaped. It's not uniform, it's not rectangular, it's not normal, it's U-shaped, which means that you have very few values that occur in the middle, and most values occur at the extremes. So instead of the curve having a peak in the middle, it has a peak at both ends and a valley in the middle. The divisor for that type of a distribution is the square root of 2. So again, we would take the half interval, divide by the square root of 2, which is equal to 1.414, and that would be the standard uncertainty due to non-standard temperature. The standard uncertainty is divided by, again, the square root of 2, the standard uncertainty is. Coefficient of sensitivity is 1 since there are no correlations with other sources. And the variance is the standard uncertainty times the coefficient of sensitivity, that product raised to the second power. You'll get tired of hearing that here shortly, I'm sure. Uncertainty of the temperature measurement device. Remember, we get that information for a calibrated device. We get that off the calibration certificate. It results from a type B analysis. Degrees of freedom is 1,000. And again, as stated previously, it's an arbitrary number. The distribution type is normal expanded, which means the standard uncertainty or standard deviation of the distribution was multiplied by the coverage factor, which in this case is 2. Standard uncertainty is the uncertainty divided by K. Coefficient of sensitivity is 1, no correlations. Variance calculated in the same manner. Okay, this is the last contributor, uncertainty due to differential temperature. Results from the temperature of the unit being calibrated and the device used to perform the calibration. Type B analysis, degree of freedom is 1,000. Distribution type is normal expanded. Divisor is square root of 3. Standard uncertainty is the uncertainty divided by K. Coefficient of sensitivity is 1. Variance, again, calculated by the same method as expressed for the other 5. Solving for the expanded uncertainty. Once the variance has been determined for each of the sources of uncertainty, the expanded uncertainty, capital U, can be calculated using the RSS, root sum of squares method. Sometimes you'll hear this as taken in quadrature. Older mathematicians tend to talk like that. We refer to it as the root sum of squares. Remember, we had taken the standard uncertainty multiplied by the coefficient of sensitivity, got that product, squared that product for each one of these 6. Now what this is saying is you sum all those squares. In other words, you take the variances and add them together, and you'll see the formula below, the root sum of squares. This is the compressed shorthand version of the equation. Here's what the equation actually looks like, with V representing each contributor, V1, V2, V3, all the way to V6. So you have the variances are the standard uncertainty multiplied by the coefficient of sensitivity, and that product squared. That would be true for V1, V2, and so forth. So you add those together, take the square root of that, and multiply it by 2. So when you take the square root, you now have the combined standard uncertainty, and you multiply it by whatever coverage factor you've chosen. And in most cases, it's going to be 2. 2 times the combined standard uncertainty gives you the expanded uncertainty, capital U. So at that point, you've got the uncertainty. Now, let's have a quiz for question 7. What is the divisor for a normal expanded distribution? Normal expanded. Keep that in mind. The poll is now open, so pick your answer for this one. Okay, let's close the poll. Bear with me a second. Okay, open the poll. Make your selection. What's the divisor for rectangular or uniform distribution? Okay, let's close the poll. All right, let's talk about part 1 for a moment. The divisor for a normal expanded distribution is K. Now we get the normal expanded distribution off the calibration certificate. We also get the coverage factor from that. And in most cases, K is going to be equal to 2. So you would take the normal expanded distribution divided by 2 to arrive at the standard deviation, or the standard uncertainty. Now, what's the divisor for rectangular or uniform distribution? That one's going to be the square root of 3. You're going to be working with either the half interval or the full interval. I'm encouraging you to use the half interval. So you would take the standard uncertainty, you take the interval width, resolution, divided by 2 to get the half width, and then divide that by the square root of 3. The other option would be to take the full interval width, which in our case would be 2.5, and divide it by 2 times the square root of 3. Now, for number 3, what is the divisor for a triangular distribution? Let's open the poll and let you pick that one. Okay, we'll close the poll and talk about this one for a bit. The triangular distribution is a distribution that occurs where it looks very much like a normal distribution. It has a peak in the middle, tapers off to nothing across the interval, much like the rectangular or uniform distribution. The difference, though, this one, the divisor, instead of being the square root of 3, it's the square root of 6. Now let's put up the last one. What is the divisor for a U-shaped distribution? Let's open the poll so you can make a selection. Okay, we'll close the poll and talk about this one now. We had said the triangular distribution has a peak in the middle, much like a normal distribution, and tapers off to nothing, which roughly approximates the curve size of a normal distribution curve that fades out to infinity. The U-shaped distribution, on the other hand, has its greatest concentration of values at both ends, and very few values in the middle. So it goes from a peak at both ends and drops off to practically nothing in the middle, then starts back up as it approaches the other extreme end. The divisor for U-shaped distribution is the square root of 2, or 1.414 is the decimal equivalent. All right, here's the answer sheet. I want to show you here that K is typically 2. We've talked about that many times, and it's found on the calibration certificate or test report. That's important to remember. The divisor for the rectangular, against the square root of 3, or 1.372. The divisor for the triangular is square root of 6, 2.449. And for the U-shaped distribution, it was a square root of 2, 1.414. These, now there are a number of other distribution types, but these are the ones you're going to encounter most often. And for instance, the U-shaped distribution is encountered in laboratories that use what's called a boundary-driven heating and cooling system, where as the temperature drops down to the low limit of the acceptable range, the heat is turned on, driving it back up. And when it starts to approach the upper limit of the temperature, acceptable temperature range, the air comes on and forces it back down. So it's a constant battle between the high and low, and it's pushed all the way to the low extreme before the heat comes on. So you get a lot of values there at the low end, and then it's accelerated as it heats and drives it back up toward the high limit. And as it approaches the high limit, the heat shuts off and the air comes on, starting to drive it back down. So you get a concentration of measurement points at both extremes and a reduced number in the middle. You get some as it's traveling from one extreme to the other, but you don't get many. So consequently, it's U-shaped. Now remember, associate that with boundary-driven heating and cooling system, where the boundary of the acceptable heating range, for instance, if it's plus or minus 2 degrees C, as it gets down to about 1.7, the heat is going to turn on and start driving it back up. And then when it gets to where it's 1.7 degrees above normal or nominal, which is 20, when it gets to about 21.5 degrees, the air conditioning comes on. Now the temperature is going to, increase a little bit more before the air starts making it drop down. So if you set the trigger points for the heating and cooling system at 2, you would actually get below 2. You get something like 17.5, and you get something on the high end that might be 22.5. So you set the trigger points, and you have to do this by experiment. You set them within the acceptable temperature range by numbers that well, even though you drift past them, you don't drift to the extremes and go out of specification for the temperature range. Now, on the opposite hand, the triangular distribution is associated with laboratories where the temperature is center controlled. So as soon as it drops below 20, the heat comes on, and as soon as it gets above 20, the air comes on, and you have the heat and the air running practically all the time, and they're battling each other, trying to maintain that exact 20 degrees. You can get a very, very tight control, and laboratories like NIST in the US or the National Physical Laboratory in Great Britain might use that in their dimensional laboratories, but they also do things like they calibrate, work on instruments to a glove box so that they don't have the technician actually in where the instruments are, and they minimize the effect of body temperature in that way. So laboratories with big budgets, or where it is absolutely essential that they have the very best performance they can, might use center-driven heating and cooling systems. Most other laboratories will use U-shaped distribution, boundary-driven heating and cooling systems. Most of you, if you're doing dimensional work, I would just about guarantee that you have U-shaped distribution for temperature because you're working with boundary-driven heating and cooling systems. Here's an example of a budget where you would populate information in here. You know, you can put on the name of the laboratory and what it is that you're calibrating, and the kind of heating and cooling system you have. I encourage you to record that because it affects how you're addressing temperature. And then this is an uncertainty budget. It might be a CMC budget where you're putting in theoretical values of the best equipment under the ideal conditions. So instead of having 19 degrees C for the calibrating temperature, it would be 20 because that's ideal. But you would take here the values you have for uncertainty, put them in this column, degrees of freedom, type of analysis, normal expanded, what is the divisor, and once you put this in, it does the calculations across here. And that's true right here. You would have, in budgets that I write, I always have a sheet called utilities, and that's where I would enter the 5 readings I took with the micrometer. It would calculate the average, the standard deviation, and from that then, and knowledge of the number of samples, it would calculate the experimental standard deviation of the mean, and that would be hyperlinked back to this cell right here. The degrees of freedom, remember I told you it's n minus 1, and we had 5 samples, minus 1 would be 4. We arrive at that using statistical methods, so it's a type A. We only calculated 1 standard deviation, not 2 or 3 or 4. The number we arrived at was 1 standard deviation from the data we had, and so the divisor is 1, and you'll see it doesn't change. The standard uncertainty is the uncertainty. Let me back up a minute. I inadvertently hit the screen and went off my slide. Okay, so anyway, the calculations take place going across here, and if you're proficient with Excel, you can write these in such a way that until you put data in, you don't see anything in these cells. Otherwise, if you have this blank or you have it full, you start populating these, you might get some an error message or something in these cells. Once all the cells would be full, you'd have the right answer. But if you're proficient and knowledgeable in using Excel, you can write these in such a way that all these cells remain empty until you fill in the last piece of information, and it populates everything. But you'll see that we have all the variances here, which is the standard uncertainty times the coefficient of sensitivity, that quantity or that product squared, and that's this number. We take the sum of all 6 of these. We get the coefficient of, we get down here, we get the effective CTE from these coefficients. That's calculated into these numbers. We wind up with a sum of variances of 1.1. Combined standard uncertainty, 1.05. Expanded uncertainty would be coverage factor multiplied by that, and we get 2.11. Right here, you'll see entered the length of the standard. We were calibrating at a length of 125 millimeters. So calculation was done based on the effective coefficient of thermal expansion to adjust that 125. And we wind up with uncertainty expressed in SI units, 2.2 micrometers. And you can have the spreadsheet set up so it records the date when the calibration was performed. You can also have, here we put in some additional information. We've identified the standard. You'll see C1, C2, all the way through C6. These are contributors, contributor 1, contributor 2. We've identified them a little bit here. We make note that the resolution is based on the half interval so that you don't forget which one you used. We enter the coefficient of thermal expansion of the standard, the coefficient of thermal expansion of the unit under test, and it calculates the effective coefficient of thermal expansion. And what you would find in this cell is the formula that I showed you earlier, taking into account a plus 7.5 and a minus 7.5%. And that's what's used to produce this. In fact, we did the calculation and got that result. So in a nutshell, there's a lot of stuff going on here. But what we're doing is those things that were outlined previously in the slides for each of the individual contributors. Now, in the comprehensive uncertainty class, this budget is developed, the automation within it is developed and so forth. So those of you who are interested, that's something that Perry Johnson will have available, I'm sure, in your neck of the woods, once the present difficulties are past and behind us, where travel is permitted and gathering together is permitted. But this is an example of a budget that would be totally self-contained and allow you to put in pieces of information that you can arrive at by straightforward means. You can find out what the coefficients of thermal expansion are. You can find out what the uncertainty from the calibration of the standard was and the uncertainty due to the calibration of the temperature measurement device. You can arrive at a reasonable number for differential temperature. You can record the non-standard temperature that existed when you performed the calibration and plug in those known pieces of information, the 5 measurements that you took, and it will calculate the experimental standard deviation of the mean. And then it will populate all of the budget to the right, filling in all that. Once the last one is filled in, it will do the calculations at the bottom and give you the measurement uncertainty of this micrometer when calibrated at 125 millimeters. Now, I'd like to say, just as a side light to this, that typically when you're calibrating micrometers, a laboratory will state on their scope the capability of calibrating, from very small to very large. Now, calibration can only be performed when you have a calibrated standard to compare to. Calibration isn't the adjustment of a micrometer or an instrument to make it inspect. Calibration is simply the comparison of that device to a device of known value. In this case, the comparison of a micrometer with unknown performance against a gauge block of known performance with known uncertainty. So because it requires a standard, you can't calibrate 0. You can verify that a micrometer will close down to 0 with nothing between the anvils. But by definition, if it's nothing within the anvils, there can't be a standard. Consequently, a scope might say that the micrometers can be calibrated from, well, let's say 1 millimeter to 125 millimeters. So they would have in essence, they'd have a 0 to 25 millimeter, a 25 to 50, 50 to 75, 75 to 100, 100 to 25. They could calibrate those 5 micrometer ranges. Now, if you take an individual micrometer and calibrate it toward the low end of its measurement capability, down around 1 millimeter, for which you would have a standard, I should say, and then you calibrate it at the high end at 25 millimeters, you can develop what's called a relative uncertainty statement, which is the uncertainty expressed in terms of a variable, and in dimensional, the variable would be length. So you might get something that would say 0.021 plus 1.32 times L micrometers. And you just plug in for L any value between 1 millimeter and 25 millimeters, and that would give you the uncertainty of a measurement taken with that micrometer at that particular value. Most people that are doing micrometers, height gauges, dial indicators, coordinate measurement machines, anything that has the potential to measure over a range of sizes rather than one captive size. Now, a gauge block will always have what's called an absolute uncertainty, because it's the uncertainty of the exact length of the gauge block, not that, not that it's adjustable within a range. It's not. It is what it is. But instruments that can measure over a range of sizes, typically the uncertainty is expressed as a relative uncertainty statement, and that way a user can calculate the uncertainty of a measurement anywhere within that range. And that's another topic that is included in the comprehensive uncertainty class. It's a topic on which I think there's some information on Perry Johnson's website that you can download relative to that. We're going to go from this point into the question and answer session. Now, questions, I'm going to read those from the screen. In other words, they're going to be typed into a box. I will read them and I will respond to those verbally. You'll be able to hear me. And hopefully we can answer your questions, and hopefully the questions we address are meaningful to all of you. Bear with me just a second. Okay, I'm going to ask you to look on the right-hand side of your computer screen. There's a question tab, and you can type questions in there. We have one. Christopher Shipman has asked a question. Could you enlarge on coverage factors, please? Yes, I will, Christopher. And if what I say doesn't answer your question, please type it again. Okay. Let's see. The coverage factor, Chris, is nothing more than the number of plus and minus standard deviations of the distribution. So if you're working with plus and minus 3 standard deviations, or a coverage factor of 3, that captures 99.73% of all values within the curve or under the curve. If you're working with plus and minus 2, it's 95.46%. We talk about an approximate 95%. Actually, when we say we have a 95% confidence level, we actually statistically have a 95.46%. So when we talk about K, we're talking about how many standard deviations of the uncertainty distribution are we talking about. And if it's K equals 2, bear in mind that's plus and minus. That means it's 2 standard deviations to the left of the mean and 2 standard deviations to the right of the mean. So the coverage factor is nothing more than the number of standard deviations or standard uncertainties of the uncertainty distribution that are considered. Again, it's a plus and minus value. So if we say K equals 2, We're talking about the percentage of the distribution contained between plus and minus 2 standard deviations. Hopefully that answers your question, but again, if you still have questions, please respond again. I'll look for your name and try to answer it. Okay, let's see. All right, I have a question. Can we talk a little bit about how one estimates the CMC? Yes, I can. I told you that basically it's a hypothetical or theoretical situation, because it doesn't really exist. In your laboratory, you don't encounter the very best instrument in its class, and no matter how good you aren't always at optimum conditions, or ideal conditions, I should say. You may be optimum in that you're controlling it pretty close. For instance, in a dimensional laboratory, temperature is controlled pretty tightly. Maybe you try to hold it to plus or minus 0.5 degrees C, which would be very good if you could. But that's still not zero. So there's still an effect due to the coefficient of thermal expansion. If your temperature was zero all the time, then differential temperature wouldn't be an issue, because the temperature would never differentiate. It would always be what it's supposed to be. But that's not the case. So you have to deal with differential temperature. In a calculation of CMC, you could say that differential temperature is zero because you're doing this at absolute best conditions, and you're calibrating the very best the very best instrument in this class. So in this case of micrometer, this is the very best micrometer of that resolution available as far as a manufactured class, and you happen to have the very best one of that class. Again, that never occurs, but the calculation is done just like you were doing an estimate of uncertainty. In fact, typically on a scope, it'll say CMC expressed as an uncertainty, because the calculation is exactly the same. The values that you put in are different. Now, you would have to come up with an uncertainty for the standard that would be used. Well, if that's your 25 millimeter gauge block, that's a real uncertainty that you have from its calibration certificate. And you also have the real uncertainty for the temperature measurement device. You also have the real value of 4 measurements. You know what that would be. You could do that, but you just don't know. Well, technically, you don't know the repeatability. You can't do that because you don't have that best instrument. But I think in that case, what I would do, I would take the gauge block and the best micrometer you have access to, take the 5 measurements, get the experimental standard deviation of the mean, and then divide it by 2. And I would note on the spreadsheet that you did this because this is a CMC calculation. Now, James, if that question is answered, fine. But if you still have questions about CMC, then let me know. Now, there's a note here. Let me read this. If a torque transducer is being used to calibrate torque tooling, would you effectively create an uncertainty budget for the specific transducer using an ideal unit under test? You would then express your CMC for that particular transducer with the resulting expanded uncertainty. Actually, when you estimate the CMC to go on your scope, if you have multiple means of performing a test or calibration, what goes on the scope is the method that produces the best result, and then looking at that method, okay, now if I'm under ideal conditions and with the best in class instrument, what would that be? In other words, it is intended to represent the very best performance you could do, meaning the very smallest uncertainty that you would generate performing that calibration or that test. So if you have multiple means of doing it, you're picking out the very best one of those, and then you're looking at that and saying, okay, now if this was using the best in class instrument, or if I was calibrating the best in class instrument and at ideal conditions, how would that affect my budget? Well, there would be no differential temperature. The calibration would be taking place at standard temperature, 20 degrees, not 19, not 21. And the non-repeatability would be a result of taking the very best instruments you have available, measuring your gauge block 5 times, estimating the experimental standard deviation of the mean, and then divide it in half, noting that that was a developmental decision to do that because it's theoretical anyway. You don't have access to the best in class equipment, and you're never going to be at ideal condition. So hopefully that was sufficient explanation, James. But if not, again, please respond and I'll try to elaborate more. And let's see, what else do we have? Okay, next question. This is a very good one, very important. If you do not add a statement of compliance on the certificate, then you do not need to state the decision rule either. And there's a question mark, so that's being asked as a question. And thanks for the question, Andy. That's an important point. And the truth is no. If your customer does not require you to state compliance with a specification, then the only thing you have to provide them is the measurement result and the uncertainty of the result. They then take those two pieces of information and they make the decision, is it within specification? Is it satisfactory for their use? You have done all that you're required to do at that point. The only time you need a decision rule is when you're going to be required to state compliance with a specification. Very good question. I'm glad you asked that. Let's see if we have anything else. Well, gentlemen, since I haven't gotten any responses from the first questions that were asked, I will assume that the answers were satisfactory. I'm not seeing any more coming up. I want to tell you I appreciate your taking the time out of your day to participate in this abbreviated training, this short course. Hopefully what we talked about is meaningful and helpful to you as you strive to develop appropriate and well conceived estimates of the uncertainty of calibrations and tests that you perform. I hope perhaps that you realize that much of what you need is in the standard, and if not, it's supplemented in the GUM, the VIM, ILAC P14, and PJLA PL3 or equivalent document from other accrediting bodies. And I want to tell you, I appreciate, especially with the difficulties that we're all facing today, that you took the time to be with us. And I tell you, or ask that you please stay safe, stay distant to the degree you can, and hopefully all this will be behind us and we can all get back to calibration and testing as quickly as possible. Okay, looks like something else just popped up. You know, the question is, can I ask one more question? Yes, you can. So what's the question, Jordan? Do you have any resource for microbiology testing? When you say resource, are you talking about something that would deal with the uncertainty of your microbiological testing results? I assume that's what you're talking about. Yes, uncertainty of measurement of results. Dave, what I would suggest, I don't want to be promoting commercial products during this test. That's not our, or pardon me, during this class. That's not our purpose. But if you can send me an email that I can respond to, I would be glad to direct you to some, what I think would be appropriate products for you that would do a good job. Do you want to give me your email address? Or I'll tell you what, I'll give you mine. My email address is alexeng25@msn.com. Okay, I'll look forward to receiving an email from you, Jordan. And I think that that's the last of the questions. Yep. That's the last of the question. Again, gentlemen, it's been a pleasure. Look forward to talking to you in the future. Perhaps we'll be doing other training that you'll want to participate in. And hopefully those of you that are pursuing accreditation will choose to use PJLA for accreditation services. Thank you very much. Oh, wait a minute. Here's another question. Oh, okay. Well, thank you for the comment. I appreciate it very much, and you're more than welcome. Until next time.